Alrighty, so today we're talking about weight. I'm going to get my prop out here. You can write down as much as you want, as always. I would suggest you write at least the sample question down that's going to be at the end. If you have an earbud in, you need to get it out. If you have a phone out, you should put it away. If you have both, you should do both. Alright, so today we're going to talk about weight changes in situations where objects are accelerating vertically. So as something is being accelerated, and the key word here is accelerated, either up or down, their weight changes. Now we've talked about already, we talked about orbiting the Earth, right? Here's the astronaut, and he's going to orbit the Earth, and I talked about how he's constantly falling, which is why you can't find out his or her weight, because the object that you're using to find that weight is falling as well. You know the guy from Veritasium, he's got a little video about mass versus weight. And oddly enough, the Australians have trouble with. Okay, so I will try to do some explanation in a Canadian accent. So an object's weight is simply a measure of the force of gravity on the object at that particular instant. Chiropractor, apparently. Object's weight is simply a measure of the force of gravity on the object at that particular instant. Since weight is a force, gravity is an acceleration, therefore, and you've seen this already, right? The weight force is mass times gravity, where FW is the weight, M is mass in kilograms, and G is the gravitational field strength. And that G on Earth is 9.8, and depending on what we're talking about, it would be newtons per kilogram, and I'm going to make a better 8. 9.8 newtons per kilogram. And I've done this before, right? I jump on here. For every kilogram that I have mass, it shows 9.8 newtons. Right? So to turn that newtons into mass, I just divide by 9.8. And it tells me what my mass is. If you want it in pounds. Now actually, technically, pounds is actually a unit of force, weight. Right? It's not a unit of mass. When you see on your tires, it'll say PSI, pounds per square inch, right? So the pounds refers to a force. It's not a mass. Doesn't make sense, right? Pounds are force. The other unit for like PSI, what's the other? Kilopascals, right? That's a pressure, yeah. Kilopascals are pressure weight, or pressure unit. Okay, so FW is equal to mass times gravity, where FW is the weight, measured in newtons. Mass is measured in kg, right? Yeah? Good? Nothing of real importance there. And obviously, the greater the mass, the greater the weight, since the gravity remains constant. So if I pick up something reasonably heavy, yeah, but I have to pick it up. If I pick up something that's reasonably heavy, like a couple of textbooks, right? And do I have more mass? I being the combined system, right? So, you know, it used to say 800, now it says 860, right? Because I got more mass. The greater the mass, the greater the weight. The less mass, when you lose weight, really when you go on a diet, are you trying to lose weight? You're trying to lose mass, really, right? Greater the weight, since G remains constant. Now, G remaining constant on Earth, is it 9.8 everywhere on Earth?
Yeah.
More or less. There are small fluctuations they're not really sure about, and it also depends on your altitude as well, above sea level. Okay, so for example, and this is basically what I was saying, when you stand on a rafting scale, the scale reads the amount of force that you are exerting on it due to gravity And then your bathroom scale at home will convert it to mass units, kilograms. Now, many of you probably have a digital scale at home. I have one. You can flip it so that it shows pounds or kilograms, right? Because nobody knows what they weigh in kilograms. The real answer is you don't weigh anything in kilograms. It's your mass. Jeff, you realize I'm teaching here, right?
Whoa.
Okay? But this weird bathroom scale measures it in newtons, right? And it says, I'll get out of the way. So the scale is measuring how much force I am exerting on it because gravity's pulling me down and pushing me against the scale, right? Newton's law says there's an equal and opposite reaction force. The scale has to exert an upward force on me. If my weight is 800 newtons, how much is the scale pushing on me, Leo?
800 newtons.
Correct, 800 newtons.
Scale 80. No. 8 times 9.8. I don't know.
You don't know because you're not paying attention.
It's equal now.
No, it's equal.
Yeah.
See, it says right there, equal and opposite reaction force. So 800 newtons down means 800 newtons down, which is why I'm not accelerating. Right? This upward force is known as the normal force, Fn. Right? And it always opposes gravity. When the surface is flat. If it's at an angle, that's not true. That's a little bit untrue. Okay, so suppose you are a weird-looking person wearing a pink shirt and yellow suspenders.
Heck yeah. Oh, yeah.
Suppose you take that scale onto an accelerating elevator. Now, this is the key. The elevator has to be accelerating. Who's been on the elevator at, say, the CN Tower? Yeah? Yeah?
I got stuck in the elevator.
Okay.
Good time.
Who's been on the elevator here at school?
That thing is
It's sketchy? It is a little bit scary. Is it accelerating, Olivia? Does it ever accelerate?
Yeah.
Yeah?
It has to
keep your server. You're absolutely right. It has to accelerate right at the start, but it basically goes from 0 to really slow, and then stays really slow until it gets to the top, and then it stops. No, most accelerators will reach a constant speed. Right? Yeah. But if you get in a tall one,
It's so hard to get in this.
if you get in a really tall one, because it has to go really fast and it's going a long ways, it accelerates for quite a while, right? So at the bottom of large elevators like the CN Tower, how do you feel?
Feel heavier.
You mean heavier?
Yeah.
Right? You feel heavier, don't you? And then what happens when you get to the top?
You feel that. It's like, whoa.
Yeah, you kind of feel a little bit lighter for a second, right? There's really tall elevators. Like I've been in a hotel in Las Vegas, same thing, really, really tall. You get there really fast, and you kind of after a big meal, and then you get to the top. Not good.
Have you ever been to Disney
Yeah.
World?
No.
Hollywood Studios has one of those tower flare ones.
Oh yeah.
You like go up fast and it just drops you down.
Scary. It was pretty good.
9.8. See, if I went, I'd be timing it and doing all physics. Okay, so here's the logic, though. Okay, here's the logic. So you ride the elevator while standing on the scale. Since the elevator and thus the scale are accelerating you up, so I'm the weird-looking guy with the pink shirt and the yellow pants, suspenders. Okay, and I'm on my elevator, and it's accelerating me up. Now, if I weigh 800 newtons, how much force is needed to accelerate me up?
More than 800.
Okay, Leo said 800. Brett's saying more than 800.
No, more.
More than 800, Leo?
Can accelerate you.
To accelerate me, there has to be a net force more than 800, exactly. Okay, so it says that right here. You ride the elevator while standing on the scale. Since the elevator and thus the scale are accelerating you up in the air, it must be applying a greater normal force on you. When I'm standing on the floor, 800 down, 800 up. Now I'm in the elevator, I'm accelerating up more than 800 up because I'm accelerating, which means, let's say 850, so we can talk about it. 850 up, I'm accelerating up. How much do I weigh?
800.
I weigh 850, don't I? How come? Equal and opposite. So if the scale pushes 850 up, I have to push 850 down. which is why I feel heavier. Because you are. It's not just a feeling, it's you are. Since you must react with an equal and opposite force to keep Newton happy, you appear to weigh more because the scale does not know the difference between riding in an elevator and a person with a greater gravitational pull. It doesn't know why you weigh more, and it doesn't care. It just says you weigh more. It just knows that you are. Okay? So, think about elevators. Where in the elevator are you going to weigh more?
When you
Bottom?
go up, when
Only,
when
like,
you're at the bottom and then
When you're going down, you weigh less because you're going down.
so going up you weigh more, going down you weigh less.
while you're accelerating
No, equal.
in the beginning,
To your top speed.
No, I'm wrong.
in the
Okay, well, okay, so Leo is right. At the beginning, when you're on ground floor, beginning, ground floor, accelerating up way more, right? We're a little bit unsure about where else, maybe. Okay, let's think this through again. What if you were to ride the elevator down? If I'm at the top, I'm out there at the sky deck, CN Tower, get in the elevator, and I accelerate down.
You'll feel lighter.
Do I feel lighter, Cole? I'm at the top. I'm just starting to go down. I'm accelerating down. Why do I feel lighter at the top?
Because it's almost like you're going down. It's almost like free
It is almost like free fall. It's taking I don't need as much because it's pulling away, right? There's not as much normal force to sort of hold me up because it's not holding me up, it's accelerating me down. Right? So it's less than 800 is needed, push on me, which means if say it's 750, if it's 750 holding me up, and I push down to 750, and I weigh less.
because you're going like you're going at the you're going same way as the gravity's pulling you, so you weigh less.
Mm-hmm.
You're not going the opposite.
Here's a little animation that shows it. Now, this is key. There are 3 states of motion during a journey elevator. There are 3. Think about getting in the elevator ground floor. The first state is accelerating up to speed. Jeff? Right? The majority of the trip is at a constant speed. And then at the end, you actually slow down. Now, that's true for just about any reaction. When I throw the ball at Brett, I accelerate at the start. As it's going through the air, it's moving at a constant speed. I know there's air resistance. And then when he catches it, he decelerates it and slows it down. Same thing, right? Same thing. Okay, so the initiate elevator, now I'm wearing a green suit. A little better dressed. The elevator is initially at rest, and then it begins to accelerate. So there's level 1, level 2, right? The elevator is now accelerating. The man feels heavier. He was holding a briefcase at the start. He feels heavier. Look, it even gets like... Why does the man feel heavier during acceleration? Draw a free body diagram. Gravity is down, right? They use W for mg. I use FW, same thing. This is just the man's weight when he's at rest. The floor of the elevator exerts a force R on the man. We don't call it R, we call it normal, Fn. Are they balanced? Are those two balanced?
No.
How come? He needs a net force. There has to be a net force so that he accelerates up. Right? In this case, the normal force R is greater than mg, and by Newton's second law, R minus mg is equal to ma, and it's greater than 0. And the net force accelerates the man upwards. And by Newton's third law, the man also exerts a force of magnitude R on the floor of the elevator, and since R is greater than mg, the man becomes heavier. Now, notice, this is key. What's the force diagram like on the man? Smaller force down, bigger force up, right? Is there a net force here? Yes, there is. There is a net force. It's greater than 0, and he accelerates up. This R, the equal and opposite, is not another R on him. It's R on the
Scale.
On the scale, there is a big, this thing right here, I'm gonna have to do it like this, right? I need that. It's not gonna let me do it, is it? It's not gonna let me do it. But that R is gonna have to be like on the floor. It's not on the man, right? Equal and opposite force, but not on the same object. Not on the same object. This can be a bit confusing. Okay, so that's during acceleration. Now what happens? Now he's moving at a constant speed. How does he weigh? How does he feel? He feels normal.
Oh.
Pun intended. Okay, moving at a constant velocity. That's the key. Why does the man weigh as if he's at rest on the ground when the elevator is moving at a constant velocity? Because the forces are equal and the net force is 0. Here's the free body diagram, right? mg weight down, normal force up. They are equal and opposite. Net force is 0. Ma is 0. The net force is 0. The man moves at a constant velocity. He weighs the same. He's got 2 eyes there. Okay, what's the third stage? When he's getting near the top, what's the third stage? Deceleration. Now he's going to weigh. See, we didn't talk about this. As we get to the top of the CN Tower, how do you feel?
Lighter.
No.
He's gonna want to keep
Brett's got it. He wants to keep moving at a constant speed, but the floor is trying to slow down, right? So it's like the floor is trying to pull away from him, which means less force. Yeah. The elevator is now decelerating. He feels lighter. Want to see that again? The elevator begins to decelerate. He's probably had a Red Bull.
Oh yeah.
He feels where he's lighter. Why? Here's the free body. Gravity is down, same amount, because he still has the same amount of mass. Right? The floor of the elevator exerts a force R, but it's less. How come? Because it's slowing down itself. It doesn't need to push as much. And now the net force is down, and the acceleration is down, which means because the R, the normal force, is less, that means he pushes less on the scale, and he weighs less. Okay? Now, what about the reverse trip? Think about this. So let's go back. We're starting at the bottom of the elevator. Jump in, it accelerates up. Immediately I weigh more. Hang in here, you guys. Hang in here. I weigh more at the start. Constant velocity, I weigh the same. At the top, I start to weigh lighter. So bottom heavier, same, lighter. Now I'm at the top, and now I'm going down. Exactly, Cole. You're lighter at the top. How come? You're trying to stay at rest. The floor's pulling away from you, right? Doesn't push up as much. So lighter at the top, constant speed, the same. And then when you get to the bottom, what happens? You're going to get heavier because it has to. Yes, you want to keep going, and the floor's saying, "Whoa, stop!" It's applying a greater force to you. Okay, so make sure you know the difference between all those three. I think that's the ball. I think. I thought there was more. I thought I could go through on the way down. It's not. Okay. Shall we do an example?
Can't play unless you finish this.
All right, so we have a man standing in an elevator. Doesn't need to be a person. Standing in an elevator has a mass of 60 kilograms. What is his weight if the elevator is stopped, accelerating upwards from the ground floor at 1.5, slowing down at 2 as it approaches the top floor, accelerating away from the top floor at 1.8, and slowing down at 1.5 as it returns to ground floor? Assume down is negative. Well, let's do A first, obviously. Let's do the easy one. No, that's not true. It's not 60.
What? How is it not 60?
Because that is his mass.
Oh gosh.
Your salty language.
So kilograms is a mass?
Kilograms is a mass.
I thought a gram was weight though.
It's mass. It's the amount of stuff. So 60 times 9.8.
Oh, you want us?
I will say this. One of the most common issues that comes out of this little section here is it negative, is it positive? I don't know, okay? Stop thinking about rules and actually think. Do I weigh more? Do I weigh less? Use comparisons and think it through and you'll be fine. So, part B is accelerating upwards from the ground floor at 1.5. So you're at ground floor and you're accelerating upwards. Immediately you should realize that he's going to weigh
How does it weigh negative?
more, heavier. It's just the direction of the force, right? Now, technically here, the normal force then would be positive 588, right? Okay? So we do have to be careful with our positive and negatives here. Not so much there, but when we get to the next section. Okay, so we know that he's going to weigh more, right? Okay. So I'm going to use FWA for my apparent weight. My apparent weight. What I apparently weigh. What I feel like I'm weighing. Poids. Okay, now that's going to be your mass times gravity, right? Plus your mass times the acceleration up. The more you accelerate up, the more you weigh. Yeah. You'll see it worded a little bit differently in the solutions because I've changed up how I sort of describe it.
Why'd you call A?
FWA, apparent weight force. What you appear to weigh. Because it's changing now, right? I need a way to distinguish between that one and that one. So, this is my mg is going to be my 588. And don't ask me if it's positive or negative just yet. Mass times gravity. The mass here is 60 and the acceleration is 1.5. And so, 588 plus, that's a 90. Now, let's stop and think. Let's stop and think. We've already agreed that as he's accelerating upwards, he has to weigh more. So how do I get a bigger number than 588? Well, I have to add 90, right? I got to weigh more than 588. So I am going to add 90, so that's going to be 678. Okay, now stop and think. Stop and think. The 1.5, what is the direction of, Junior, stay with me here. Tough stuff. You guys got to stay with me. You can't jump on and off the bus and expect to get to the same destination. Stay on the bus. The 1.5 is the acceleration. That is up, right? But this 588 is times mg, that's minus 9.8. How come this one isn't negative? Well, really what we're talking about here is not mg, it's really the equal and opposite, right? It's really the normal force that we're talking about here. And again, I understand people get, oh, I don't know, I just want a rule about when it's positive and negative. I'm not going to get you one. You're going to have to think. Okay, I explained to Livy the other day, it's no different than saying, I've never driven from Brandon to Souris. I've driven from Brandon to Carberry. How can I possibly get to Souris? It's the same thing. You know, you hang on to the steering wheel, you speed up, you slow down, you turn right when you need to. You can do it, right? Stop and think. It's a new situation. Say again?
How does that make sense of the normal force should do there?
If this is minus 588 and this is positive 90, I'm not going to get a bigger value than 588, am I?
Oh, yeah, you will.
No, I won't. I have minus 588 plus 90. I'd be at minus 490. Yeah. Right?
Okay, I see what you're saying.
Right?
So that's how you can.
Right. So stop and think. Okay. So now, C, slowing down at 2 meters per second as it approaches the top force. Slowing down at the top. Weighing more or less? Less. Less. So you're going to subtract.
Is it just the same formula?
Yeah, so your apparent weight force, FWA, is just going to be mg plus ma, and there's a variety of ways you can show this. So again, 588, but because I'm weighing less, which direction is the acceleration at the top? Down.
Plus
60 times 2? Yeah. Minus
where do you
2.
get 60 from? Oh, so it's from that. I got
Okay,
it.
you forgot to put newtons on the.
Yeah, you're right, newtons.
the-
So 588 minus 120. It's the same one, Olivia. Is this not the same as this one? Well, I kind of just sort of made it up. I mean, I know how to do it, right? I haven't, yeah, does that bother you that I just give you a formula?
No, but.
Yeah.
That's okay if it bothers you. It should bother you because it's like, why is it like that, right? Yeah, this one's kind of hard to derive and show. It causes more issues when I do that.
Straight out of the supermarket? Okay.
So 588 minus 120 is going to be
Safety's off.
4. Oh, it's not 588. Oh yeah, it's 588. 468. Do I weigh less?
You apparent.
I apparently weigh less for that brief interval of time.
Wait, what did you weigh? If weight is-
Well, it depends on what you describe as your weight, right? If your weight is the pull of gravity on you, no, you still 588, right? But if your weight is what a scale says you weigh, then it is.
So isn't weight just a force?
Yeah.
So then it is.
Okay. It depends on who's doing the measuring, the scale or someone off.
You don't change.
You're right, you don't change the mass. Yeah. We're getting into some pretty heavy stuff here. All right. How about you guys try, because you've got lots of space if there's a mistake, you guys try D and E. You guys try D and E. I'll give you a couple minutes.
I don't know how to do it.
Coming down.
Okay, here's D. So in part D, accelerating away from the top floor at 1.8. Accelerating away from the top. Going down. Weighing more or weighing less? Think about yourself at the top of the CN Tower. The elevator pulls away from you. You weigh less. You weigh less at the top as you pull away. Write the same thing. FWA. What does it stand for? Apparent weight force. Mass times gravity. Mass times G. Hi. Cole needs to listen. And I've already stopped it. You don't need to keep it going. Mass times gravity is our, again, 588. Which direction is the acceleration now this time? I'm going down, right? I'm going down. 60 times minus is at 1.8? Minus 1.8. So that's going to be 588 and 60 times 1.8? How much? How much? 108? So I'm subtracting 108?
I messed up. Oh,
Is that right?
Yeah.
588 minus 108 is going to be 400, is it not?
Our sheets. It's
690.
Oh.
480. Yeah, it's 480.
480. Right.
It's because you're accelerating down from the top. So you're
Yeah. Yes.
down.
The 588
You're
at
allowed.
108 is not.
It says it right there.
Is it not what? No. 588 minus 108? Why was that negative?
Because you're going down.
Like the part above it, you get like a negative one.
What do you mean by the part above it?
Yeah, and it does better on negative.
What do you? What value is negative? You took 588 minus 108 and you got negative?
0.8.
Yeah. Okay. And I have it negative 108.
I'm so confused.
I'll come by, sir.
Negative is a factor.
Sir, I'll come by. I'll come back. Okay, let's look at E. What's happening in E, Brandon? What's happening in E? Slowing down at 1.5 as it returns to the ground floor. So you're getting near the bottom of the elevator and you're feeling heavier. Visual. Brandon, stay with me, man. You gotta stop the conversations. I didn't. I literally went from here and I said I'm getting heavier, and then I stepped over here and so that's your cue to start talking. I didn't talk for like less than a second. That means you can start talking. Is that what you're trying to tell me? Thank you. It's like you guys don't know how to be students. It's a hard class. You have to work at it. Having side conversations is the number one worst way to go about it.
I'm waiting for the next question.
I know. I'm still trying to make a point. Yes, Leo.
Why are we using the force net instead of the force of weight?
What do you mean?
Like, we're using the positive force.
Okay, Jeff, I just finished talking to him about something. Now you're having a side conversation. Leo's got a question that's about this. What possibly could you be talking to Brian about? Would you like to share? He shouldn't say anything. If he wants to say you're special, wait till break. Wait till there is an opportunity in the class where we're not doing some learning. Yeah, you're right, and I get after other people too. And sometimes it's the last person that gets yelled at. Sometimes my patience just wears out, friends. The more you talk, the more likely you're going to be the one that's going to be the last one. Simple statistics and probability. Well, that's to get the last word in, right?
Well, I don't know if you're talking about
I am. Stand right here, guys.
Keep going.
Okay, Leo, can I answer your question?
No, why you not
No,
look at that?
Oh, yeah. Why are you using the force net instead of the force of weight?
Can you explain on that a bit? What do you mean?
Like, why are you using the red one instead of the black one?
Oh, okay. Yeah, it's not F net, it's the normal force. Good point. Okay? And this was asked, he's going back, he's saying, why are we not using minus F, why are we not using minus 588 over here, okay? If we use negative here, and see, and I always struggle with explaining this, Leo, so I'm glad you asked. It's really hard to explain this without getting so complicated that I confuse kids. So my strategy is always, make them think about where do they weigh more or less. We've already established in part B that we're accelerating upwards, and so we feel like we weigh more. Would you agree with that? At the bottom, when you first jump on the scale, you accelerate up, you feel heavy. Heavier than 588, right? Okay, now there's two 588s. There's the 588, which is the force on me, which is down, gravity, but then there's really 588 that I'm pushing on the scale, right? And the scale pushes up at 588, positive. Okay? So if what I'm saying is, and this is the complicated part, if this was negative 588, and because this is 60 times positive 1.5, because that 1.5 is up, then I'm going to end up with, and I'm going to do it in red here because I'm going to erase, if I had minus 588 in there, would I get 678? Would I weigh more? No, in fact, I would weigh less. I would have minus 588 plus 90, I'd be minus 498. Right? I'd weigh less. That's why we have to use this one. And it's the best way that I've found to explain it.
What's the other explanation?
It's too complicated and long.
So
Okay? I mean, I've kind of alluded to it. It's got to do with what force you're talking about, and it's not easy to explain.
Honestly, to me, that was just like a bunch of words that I didn't get.
Yeah.
All you have to know is when you're at the bottom, you weigh more or less. So make the number more. Does that not make sense?
That makes sense.
If you have to weigh more, make the number more. Right? If you owe $100 and you only got 80, you need more. Make it more. Right? So to make it more, I have to add 90.
You can't people that owe me money.
Right? If I have to make it more, add 90. Does that answer your question, Leo? Sort of, kind of? Okay, so let's go to E now. Slowing down at 1.5 as it returns to the ground floor. So again, I'm in the elevator, I'm coming down, I feel heavier. I've got to make it more than 588. How much more? FW. Okay, I'm going to need more than that. I'll need a number. So same values. 588. Right? And if I always use that 588, then it works out for me. And my mass is, 60. My mass is 60, and I'm slowing down at 1.5. Negative 1.5. Because I got to make you weigh. Hang on. I got to make you weigh. Slowing down. The acceleration is up, not my negative. I'm going down, but the acceleration is up. I'm going down, the acceleration is up. Right. I gotta weigh more. See, I'm just modeling that thinking. I have to weigh more. How do I make myself weigh more? You add. So 588 plus 60 times 1.5 is 90. So I'm weighing more, 678 newtons. I'm weighing more. You have to make it bigger. You feel heavier, okay? Draw yourself an elevator over here. Actually, leave enough room for two of them. Here's the elevator. At the top, when you're going up, you're going to weigh more. When you get to the bottom, when you get to the top, but still going up, you're going to weigh less. Right? At the bottom, you weigh more. You're being accelerated up. At the top, you weigh less. What happens on the reverse trip? Well, you start at the top, and you're going down, so you weigh less, and when you get to the bottom, you feel heavy. So really, when you put it all together, you weigh more at the bottom, you weigh less at the top. There's what it boils down to. Make the numbers work.
It is a circle.
Okay. It's a pattern. It goes up and down, I guess. I don't know if it's a circle. All right. That was, I realize that's a fair bit of correction on Friday. So you now have this one here with the ant in the corner, right?
That's actually, I think that's true.
What's that?
That ad?
Yeah.
That's interesting.
It is interesting, yeah, because they reach total velocity so quick, they just fall really, really slow for a really long time, and just no problem. Hang on. Okay, so now you can do all the questions that are labeled what? All the questions that are labeled with weight in capital letters, you can now do. I'll say it again. Now you can do all the questions that are labeled with capital weight. Okay? Pre-test number 2 coming Monday. I did. Sure. Okay. Press stop here and then I'll be right there.
Thanks.